I am a tiny ant, but I can do incredibly big things. Today, I will tell you how
I can lift 50 times my own body weight. Do you want to know the secret behind my superhuman?
Look at a single ant, and its movements seem entirely random, a chaotic series of false starts and overlapping errors. But scale that up to a colony of thousands, and the swarm processes environmental data with the efficiency of a highly tuned computational engine. To test the limits of this collective processing power, we can observe a closed biological assay. A system containing exactly 1,000 ants is introduced to an enclosure featuring 4 distinct engineered hazards. To survive, they must navigate excavation, traverse vertical drops, degrade physical barriers, and mitigate adhesive surfaces. Ants coordinate through stigmergy. As agents move, each dot leaves a fading chemical trail. When a path yields food, returning ants overlap pheromones. As more follow, the trail thickens into a solid route. Hitting a novel physical barrier, the organized line instantly shatters into chaos. In these moments of algorithmic collapse, the colony does not rely on collective logic. Instead, it depends entirely on the statistical anomaly of a single isolated scout randomly discovering a hidden bypass. By tracking how stigmergy breaks down across 4 extreme environments, we can pinpoint the exact threshold where the swarm's logic fails, and individual ingenuity is required to save the system. The baseline control for this system is a 2-dimensional sand enclosure. The swarm must excavate subsurface tunnels to reach organic payloads buried at the bottom. Individual agents approach this material displacement by acting as independent microdrills. Each ant mechanically removes a single grain of sand at a time. To conserve the colony's overall energy, the swarm employs task partitioning. Specialized roles emerge organically. Some agents isolate the labor of digging at the tunnel face, while others dedicate themselves entirely to transporting that displaced material to the surface. Working simultaneously, the swarm requires just 8 hours to establish a fully functional subsurface foraging network. This abstract spatial model maps the downward tunnel expansion over 8 hours. The layout is highly optimized, minimizing travel distance to the payload. Yet overlaying the actual movement vectors of individual ants during construction shows erratic, disorganized input. There's no guiding blueprint. Operating within the familiar parameters of dirt and gravity, the swarm's decentralized algorithm yields near-perfect efficiency. The environment naturally guides the collective behavior, requiring 0 individual ingenuity. That efficiency collapses when the environment restricts movement. The second assay introduces a vertical traversal trap, requiring the colony to cross a narrow suspension cord over an open pit. To force the ants onto the cord, the vertical walls of the pit are coated with fluon, an invisible, frictionless synthetic compound that prevents normal climbing. The initial discovery rate is incredibly fast. The first biological agent locates the suspension route within 10 seconds of entering the chamber. What follows is an immediate systemic failure. Hundreds of agents crowd the entrance simultaneously. Severe traffic jams form, eliminating coordination and pushing a high volume of ants directly into the fluon trap below. This pheromone heat map demonstrates the failure point. The narrow cord prevents proper diffusion. Signals overlap densely, flaring into a chaotic red bottleneck and breaking communication. To restore the algorithm, the path is widened and stabilized. Watch the red zone consolidate into a clean green path. Even during the gridlock, one statistical anomaly emerges. A single scout manages to cross the gap and successfully isolate a small payload that it can carry alone. While the rest of the colony is trapped in a feedback loop of overlapping pheromones, this solitary scout bypasses the swarm. It calculates its own return route, carefully navigating back across the tightrope without any reinforcement or assistance from the collective. When physical constriction destroys the swarm's chemical network, collective logic becomes a liability. Survival must be entirely outsourced to the stochastic ingenuity of an isolated agent. The third assay tests exactly how that individual ingenuity interacts with a physical puzzle. The payload is a cluster of seeds placed inside a sealed paper vault. Upon discovering the vault, the swarm completely fails to evaluate it. Hundreds of ants walk directly over the paper, ignoring the physical barrier and the payload inside. Ant colonies do not cognitively assess physical geometry to solve puzzles. Without an external chemical attractant indicating a resource, the behaviors required to breach the structure remain dormant. To trigger those algorithms, a specific chemical intervention is applied. The exterior of the paper vault is saturated with a sucrose water mixture. This application of sucrose triggers an aggressive foraging response. We see the mandibles tearing at the surface as the ants prioritize consuming the sugar, with the vault's eventual destruction being a secondary result of this feeding. The act of accessing the vault is a mechanical byproduct of this consumption. The aggressive foraging unintentionally degrades the damp paper's structural integrity, eventually tearing a hole just large enough for a single agent to slip through. Environmental problem solving is a biological illusion here. The breach is a mechanical side effect of chemically driven foraging, occurring without any cognitive evaluation of the vault's geometry. The final and most lethal hazard introduces a wide horizontal barrier covered in extreme synthetic adhesive. To provide a mechanism for survival, the system is supplied with loose environmental modifiers, scattered particulate matter, threads, and rigid wood fragments. Two distinct survival strategies emerge simultaneously. The first is, again, a pure statistical anomaly. A single agent walks directly across the adhesive surface. This direct traversal involves no pathfinding or algorithm. The agent manages to pull its legs free through sheer physical strength and biomechanical tolerance, barely surviving the crossing. While one ant uses brute force, the broader swarm initiates a different protocol. This computational model shows agents pushing particulate vectors onto the red hazard layer. Through localized interactions, these tiny deposits form a solid bridge, organizing chaotic movement into a secure path. This emergent tool use radically optimizes the route. By covering the adhesive entirely, the collective engineering eliminates the risk profile for the remaining 999 agents. Faced with a catastrophic synthetic hazard, a resilient biological system bifurcates its strategy. It allows individual agents to brute force a solution on their own, while the collective simultaneously engineers a sustainable macro infrastructure for the rest of the colony. By mitigating all four synthetic hazards, the surviving swarm successfully secures its payload and settles into an upgraded, hazard-free biological enclosure. When we aggregate the data from these four assays, the concept of the colony functioning as a unified top-down genius is easily disproven. On the left, we see high-attrition scatterplots and isolated spike anomalies representing the scouts. On the right, the smooth, mathematically efficient curve of the finalized colony path. Spontaneous physical problem-solving across the entire swarm is statistically near zero. As the graph flares with distinct chemical markers, we see that the swarm relies entirely on chemical motivation to trigger material manipulation. However, without an isolated anomalous agent randomly breaking the initial barrier and mapping a route back, the collective algorithm remains trapped in a stalemate. The mathematical perfection of the finalized route depends on this high-attrition process of trial and error. These individual failures serve as the necessary data for the collective algorithm to identify success. The final distribution of the biological reward, a high-yield strawberry payload, locks the newly engineered pathing into the colony's chemical memory. The ultimate survival of any complex swarm system is found exactly at this intersection, a few random biomechanical anomalies pushing through the chaos, continuously reinforced by the strict